Hello everyone, my name is Mamohin. Welcome to today's presentation on mass spring damper system. This session will cover engineering vibrations, followed by mass spring damper system, then its mathematical modeling and simulation. Finally, I will cover experimental study of mass spring damper system. What is vibration? Vibration is the study of the repetitive motion of objects relative to a stationary frame of reference or nominal position, usually equilibrium. Vibration is evident everywhere and in many cases greatly affects the nature of engineering designs. The vibrational properties of engineering devices are often limiting factors in their performance. For example, the poor ride quality of an automobile or motorcycle due to unwanted excessive vibration. When harmful, vibration should be avoided, but it can also be extremely useful. For example, in the case of music, vibration, say of a string instrument such as a guitar, are desirable. In either case, knowledge about vibration, how to analyze, measure, and control it is beneficial. Everyday experiences are full of vibration and usually ways of mitigating vibration. Automobiles, trains, and even some bicycles have devices to reduce the vibration induced by motion and transmitted to the driver. One of such systems is mass spring damper system. This system can be modeled mathematically based on fundamental principles such as Newton's second law of motion and analyzed using results from calculus and differential equations. Nowadays, mass spring damper systems are generally present in pretty much every vehicle you drive on a daily basis. It contains a mass, spring, damper, and induced force and displacement. Let's look at the undamped vibration on the left. Let's assume you have a spring connected with a mass. You induce force on the mass and it starts to oscillate. The vibration will continue pretty much forever. Now let's look at the damped frequency on the right. You add damper in the system and it starts to absorb or dissipate the energy out of the system. As a result, the vibration starts to decay until it dies off. When you are driving your car and you go through a bump, you require a little bit of oscillation. However, you don't need that oscillation forever, right? That's why you have mass spring damper system to take care of the unwanted vibration. Let's look at the free body diagram of the mass spring damper system. It has a mass which is denoted by M. K and B are spring constant and damping coefficient respectively. If we pull the mass with force F and give a displacement of x, then the spring and damper will try to resist the pulling force. By using the Newton's second law of motion, we can balance the force on both sides of the equation showed. Here, x dot and x dot dot are velocity and acceleration. This can be obtained by differentiating the x for a particular time. By rearranging the equation, we can take the acceleration on the left hand side. Using Matlab Simulink, we can simulate the mass spring damper system. If you look at the block diagram, you can see that it's the representation of the equation above. The integration of x dot dot gives x dot and the following integration of x dot gives x. By multiplying the x with the k, we get spring force, and by multiplying the b with x dot, we get the damping force. Eventually, by summing up all the forces, we get the mass spring damper system. We can also display results of displacement, velocity, and acceleration for different conditions. For example, if we take B as 0 or no damping condition, then the displacement versus time graph shows undamped continuous frequency. On the other hand, with a particular B value, the displacement and time graph shows damped frequency. Using the simulation result, we can select an appropriate spring and damper for a specific application where mass and induced force are known. Let's look at the simulation of mass spring damper system in depth. We have M script written on the top left hand side, which contains the inputs of the mass spring damper system. Then we have the Simulink block diagram on the top right hand, which represents the mass spring damper model. The M script code is written in a way that it can call the Simulink model while running the simulation. The bottom graphs from left to right represent acceleration, velocity, and displacement versus time responses, respectively. Let's look at the input values. Here, mass is 1 kilogram, spring stiffness is 20 Newton over meter, damping coefficient is 0.2 Newton second over meter, and pulling force is 1 Newton. We can change the damping coefficient to 0 to see its effect. Let's change the damping coefficient to 0 and run the simulation. We can see that all the graphs show undamped frequency as expected. If we maximize the displacement versus time graph, you can see the response in details. It is showing an undamped frequency. Let's minimize it and change the damping coefficient to 0.1 Newton second over meter and run the simulation again. All the graphs at the bottom show damped frequency this time due to the application of damping coefficient. Let's maximize the displacement versus time graph to see the response in details. You can see that the damped frequency response. Let's minimize the window and again run the simulation with larger damping coefficient of 1 Newton second over meter. This time, the graphs at the bottom showed quick damping. Let's maximize the displacement versus time graph to see the response in details. You can see that the frequency got damped very quickly compared to the previous condition of damping coefficient of 0.1 Newton second over meter. Therefore, by applying this simulation, we can very quickly and easily find appropriate damping coefficient for a specific application. So far, you have gained a detailed knowledge of mass spring damper system. Now, let's look at the experimental study of this system. We can use TM155 vibration test rig in this purpose. This test rig contains mass and force generator, rigid bar, damper, control unit and display, sensor and spring. Therefore, it has all the elements necessary to study mass spring damper system. Let's assume that the mass, force and spring are constant. By changing the damping media, which can be of different types of oils with varied viscosity, we can induce different damping coefficient. After running the test with induced force, we can obtain the displacement versus time response as shown in the figure on the right hand side. In the graph, we can see that A showing undamped frequency, B showing the slow damped frequency, and C showing relatively quick damped frequency. The change in these frequencies can be explained by the different damping media used in this experiment. We can also compare this experimental result, let's say for example the displacement versus time response with the displacement versus time response obtained from the simulation results and find the experimental errors and also identify the cause behind these errors. I hope you enjoyed the presentation on mass spring damper systems. Thank you.